All right, so now that we've gone over confidence intervals for a population mean, we also need to talk about confidence intervals for both population proportions and for standard deviations. So recall from the last video that the general form for a confidence interval is some point estimate plus or minus the margin of error. And this margin of error is found by taking the critical value that we need times the standard error. Standard error. So when we're talking about population proportions, our point estimate is going to be the sample proportion. So remember that p hat is our sample proportion, and this is equal to x over n, where x is the number in sample who satisfy whatever criteria we're making a proportion for. So the standard error and the critical value are going to be determined by the sampling distribution of the point estimate. So here, when we have a sampling distribution for p hat, it's going to be approximately normal if n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. In other words, p being our proportion of success, n being our sample size, we need at least 10 successes and 10 failures in order for us to have something that's approximately. And then our standard deviation for p hat is going to be square root of p times 1 minus p over n. So typically in practice, so this is our standard error. Well, typically this is our standard deviation for the proportion. So in practice, we don't know p, kind of why we're making a confidence interval for it. So we'll use p hat to find the standard error. And so that will be the square root of p hat times 1 minus p hat over n. And so then our confidence interval for p is going to be p hat plus or minus z sub alpha over 2 times the square root of p hat times 1 minus p hat over n. So when we're making a confidence interval for the population proportion, we're making the following assumptions. First, we have a simple random sample. Second, our population is at least 20 times as large as the sample. So we need to have our sample really be a very small portion of the population when we're doing this. The items in the population are going to be divided into two categories, so a success category and a failure category. And the sample must contain at least 10 individuals in each category, and this is so p hat is approximately normal. All right, so let's go through an example. A simple random sample of 200 third graders in a large school district was chosen to participate in an after-school program to improve their reading skills. After completing the program, the children were tested, and 142 of them showed improvement in their reading skills. We want to find a point estimate for the proportion of third graders in the school district whose reading scores would improve after completing the program. So P hat here is going to be the number that improved, 142, over the total number, which is 200, and so we'll get 0.71. And now we want to construct a 95% confidence interval for the proportion of third graders in the school district whose reading scores would improve after completing the program. So here, similar to before, we know we have a 95% confidence interval. That means we'll have 0.025 on the left, 0.025 on the right, and that means we're trying to find z sub 0.025, which will be equal to the inverse norm of 0.95 plus 0.025, 0, and 1, which will be approximately 1.96. And so when we want to construct our confidence interval, we'll take 0.71 plus or minus 1.96 times our standard error term, which will be 0.71 times 1 minus 0.71 over 200. And so this gives us 0.71 plus or minus approximately 0.0629. And so then our confidence interval will be 0.647 to 0.773. And so we are 95% sure that the proportion who improve their reading skills is between 0.647 and 0.773. So would it be reasonable for us to include that more than 60% of the students will improve their reading scores after completing the program? Well, if we're 95% sure that we're between 64.7% and 77.3%, I'd say that would be pretty reasonable for us to include. So yes, C above sentence. So our district superintendent wants to construct a confidence interval for the proportion of elementary school children in the district whose scores would improve. And we want to know whether or not we could use this sample. So let's think about this for a second. Let's review what we have here. So the district superintendent wants to use this for all elementary school children. But when we look back at how the problem was initially stated, we're only talking about third graders, not just elementary school children in general. So it's okay to use this for third graders. We should not use this for just elementary school children in general. So since this sample only includes third graders, so this is not a good representation of all elementary school children. So sometimes we've got a specific value, m, that we'd like for our margin of error to be, and so sometimes we want to compute a sample size n that's likely to give us that margin of error size. So remember, our margin of error is that thing that we're subtracting that plus or minus part. So note that our margin of error is going to be m, which in this case is z sub alpha over 2 times this standard error, p hat times 1 minus p hat over n. And so we could do a little bit of algebra if we're saying, instead of me trying to find the margin of error, I want to go ahead and get a specific margin of error and specify what that is, then this z hat's not going to change. This z sub alpha over 2 won't change. And so the thing that we need to adjust then would be our n. And so if we want to go ahead and solve for this n, we could divide both sides by z sub alpha over 2 and then square them to get something that looks like m squared over z sub alpha over 2 squared equals p hat times 1 minus p hat over n. And so here, if we want to try to solve for n will end up being p hat times 1 minus p hat times z sub alpha over 2 over m, whole quantity there at the end squared. And so we want to go ahead and try to figure out then, based on what we know our margin of error is, what our sample size should be. Now granted, we won't always know what this p hat is. Typically what we might have to do is find some way of getting, say, the worst case scenario. So let's talk about that a little bit. So what we're going to see is that our sample size, if we're trying to find our specific margin of error, it's going to rely on the margin of error and the sample proportion p hat. So here's the problem, is that when we draw a new sample, p hat should change. And so we don't necessarily know what p hat's going to be. So we have two ways to determine what we should use as p hat when we're trying to figure out the sample size. So recall that this is typically going to depend on n. So one is we could use a value from a previously drawn sample. And this could work. Maybe we could use a previously drawn sample, and that will let us get an estimate for what we should make our sample size be. And sure, we won't get the same p hat in the end, so our margin of error might be a little off. But maybe that's okay. Maybe it's not. So what we want to do, maybe to make sure we can handle the worst case scenario, is this second option, which is to assume p hat equals 0.5. So what this is going to do is it's going to make the margin of error as large as possible for any sample size n. So let's kind of review this claim for a second. So let's go back to the previous page and look at this formula here. So we're saying that when we're looking at n, which is going to be determined by taking p hat times 1 minus p hat times this part here, we know we're looking for a specific margin of error, and we know we have a certain z sub alpha over 2, and then we're squaring that. So this part's locked in. We're not going to worry about this part. We want to make this as large as possible. And so we do that, and then we can make sure our sample size is big enough that we're gonna be able to satisfy the worst case scenario. So 0.5 times 0.5 is 0.25. We would say 0.4 times 0.6 as an example, we get 0.24. And so if we change these numbers, even 0.49 times 0.51, we're going to get closer and closer to 0.25, but 0.25 is that maximum value we can get when we're looking at this p hat times 1 minus p hat. So if we deal with the worst case scenario, then we're going to be able to make sure we obtain a certain margin of error or something that's smaller than that margin of error, right? We're okay if the margin of error shrinks, but we don't want it to get bigger, right? We want to make sure our intervals are as small as possible. And so that's why we want to specify a certain margin of error. All right, so let's tackle an example then. So in a survey of 800 parents, 632 said that music education has a positive effect on academic performance. We want to estimate the sample size we would need so that a z of 0.025, and so we want to go ahead and take the inverse norm of 0.95 plus 0.025, 0 and 1, and we get approximately 1.96 as that value. We want our margin of error to be 0.025. And if we want to go ahead and look at using p hat, so let's say we wanted to use p hat. Here we're saying that we have 632 over 800. So if we want to use this first method, then we should have 632 over 800. That will be 0.79. And so in order to find n, we'll take p hat times 1 minus p hat over z sub alpha over 2 over m times z sub alpha over 2 over m squared. So this will be 0.79 times 1 minus 0.79 times 1.96 over 0.025 squared. So it'll be 1019.71, which will round up to 1020. So let's review what we've said. We said that we had a survey of 800 parents, and 632, so about 79%, said that music education had a positive effect on their academic performance. And so what we calculated is that if we had a sample size of about 1020, we would expect the margin of error to be very small, so that we would end up having something that varied above and below by no more than 0.025. We only have 800 people, not 1,020. So we're using this survey as a guesstimate for what we think the overall impact would be. And so we can't really use this as our exact margin of error. So let's say we want to construct a 95% confidence interval for something else. So we want to look at a 95% confidence interval for the proportion who believe physical education has a positive impact on academic performance. And we want to estimate our sample size needed for a 95% confidence interval with a certain margin of error. So here, in this example, we don't have a p hat to use. So we'll use the worst case scenario of p hat equals 0.5. And here we also note that m is 0.025, and so when we go to solve for n, p hat times 1 minus p hat times z sub alpha over 2 over m squared, that'll be 0.5 times 1 minus 0.5 times 1.96 over 0.025 squared. And so here we'll end up getting, let's do that really quick, 0.5 times 1 minus 0.5 times 0.96 over 0.025 squared. When we round up, we'll get 1,537. And so this here is going to be a guarantee that the margin of error will be no greater than 0.025, no matter what p hat actually is. So that's pretty neat. All right, so we've talked now about confidence intervals for means and for proportions, but what we haven't talked about yet is how we could find a confidence interval for the variance or the standard deviation. So although most confidence intervals are constructed for means and proportions, when the population is normal, we also could go ahead, I'm going to underline this, when the population is normal, we also could go ahead and construct confidence intervals for both the standard deviation and or the variance. And so here, these have a different distribution than what we've seen so far. So this is going to be following something called the chi-squared distribution. So here, this is the Greek letter chi. Looks like chi, it's chi. So just like with the student's t distribution, there's many of different chi-squared distributions, each with a different number of degrees of freedom. So here we've got one that is 1 degree of freedom, 5 degrees of freedom, 10 degrees of freedom, 20 degrees of freedom, 30 degrees of freedom. And so some important things to point out here, the chi-squared distribution is skewed right. And our values in the chi-squared distribution can't be negative. They start at 0. That makes sense for a standard deviation and a variance because you can't have a negative standard deviation. Now, something else that we will note about the chi-squared is that the mean of a chi-squared distribution is equal to the number of degrees of freedom that it has. So our critical values are going to be based on a certain confidence level, are going to have the same idea as before. So we'll have 1 minus alpha be in the middle, and we'll have an area of alpha over 2 on the left and an area of alpha over 2 on the right. And so we'll end up with a chi-squared cutoff for 1 minus alpha over 2 and a chi-squared cutoff for alpha over 2. So here, our confidence interval in this case looks different since chi-squared is not symmetric. So let's say we wanted to find the critical values for a 95% confidence interval using the chi-squared distribution with 10 degrees of freedom. So let's kind of point out some nice features of the chi-squared distribution. We'll have this 0.95, the 95% middle here. The mean will be somewhere around here. Since we're looking at 10 degrees of freedom, the mean is 10. And we have 0.025 or 2.5% of the area on the left and 2.5% of the area on the right. And our cutoffs here are chi-squared of 0.975 and chi-squared of 0.025. And so here, for now, I'm going to just tell you what these end up being. So the chi-squared 0.025. Here we would use some sort of inverse chi-squared function. We don't have that on our calculator, so you'll kind of be seeing in the next couple of weeks how we're going to use chi-squared a little bit with a table. And so once we get to how we use that table and such, then we might worry about these things. We won't be spending a lot of time in problems and practice working on the standard deviation confidence intervals, but they're kind of nice to see that we can do. And so we have these different values for our cutoffs that we're looking at. And so if we have a sample of size n that's drawn from a normal distribution, the quantity n minus 1 times the sample standard deviation squared over the population standard deviation squared is going to approximately be equal to these chi-squareds of n minus 1. And so here are critical values. Are taken from the chi-squared distribution with n minus 1 degrees of freedom. And so here, this quantity is going to follow a chi-squared distribution with n minus 1 degrees of freedom, and therefore a proportion of 1 minus alpha of all possible samples. When we're looking at our confidence interval for standard deviation, this is a little bit contrived to derive. So we'll see that our standard deviation ends up being between the square root of n minus 1 over s squared over the chi-squared for alpha over 2 on the lower end, and the square root of n minus 1 over s times s squared over the chi-squared value for 1 minus alpha over 2. So again, it'll be helpful if we can know what these values are, and we will see something for this at some point in the future, although I wouldn't expect to be working on a lot of these problems, say on a mastery exam or on a review assignment or a homework, for example. These are just some nice things to see since we're talking about confidence intervals. So let's say we're looking at the compressive strengths for 7 concrete blocks, pounds per square inch, being measured with certain results. We're going to assume these values are from a simple random sample with a normal population. What we want to do is we want to look at the confidence interval for the population standard deviation. So here s squared is going to be 2699.86, our sample variance. our n is equal to 7, so our degrees of freedom is 7 minus 1, which is 6. And so looking then at how we would normally draw our curve, we'll have a chi-squared value of 0.99 on the left, a chi-squared value of 0.01 on the right, and 98% sitting here in the middle. And so we would need to find ways of getting the chi-squared for 0.01, which is going to end up being 16.812, and getting the chi-squared for 0.99, which is 0.872. And so here, our lower bound will be determined by taking the square root of 7 minus 1 times 2,699.86 over 16.812, be approximately 31.041, and the upper bound for our interval, if we wanted to go ahead and calculate it, will be 7 minus 1 times 2,699.86 over 0.872, and this is approximately 136.298. So we are 98% sure that our population standard deviation is somewhere between 31.041 and 136.298. So that would be our confidence interval. Again, in order to do this, we would need to know how to calculate these chi-squared values without me just handing them to you. And when chi-squared becomes a more important thing for us later in the semester, I'll be giving you kind of a table that helps with that, because I know not all calculators have ways of doing the inverse chi-squared. So that's it for today, for this video. Stay tuned, and I'm sure we'll see more real soon.